just said find those derivatives, and that's again a big part of what we did in chapter 3. So derivatives aren't going away, we're just now applying them in new ways. In 5, 6, 7, and 8 you were matching, so you didn't need a lot of work for those. And then in 9 and 10 you were telling me about their limits. So we had to go back and recall how to find a limit. And then in 11 and 12, we were finding derivatives as well as domain and derivative formulas. Okay, from the other day, we did 1 through 4. So in 1 through 4, it said find the extreme values and where they occur. So you were looking at those graphs and you were looking for your extremas. So in number 1, since that's a closed circle at the beginning and the end, this is a continuous graph. We have a continuous closed interval. Therefore, I am guaranteed an absolute max as well as an absolute min. So the mins occur at -2, 0, and 2, 0. The max occurs at 0, 2. Number 2, this is not continuous. Therefore, I am not guaranteed absolutes. I am, however, able to look at the graph and find local. The local cannot occur at the open circles. Therefore, I have a local min at -1, 0 and a local max at 1, 0. Because that is the lowest point relative to what's happening around it. That is the lowest point relative to what's happening around it. Number 3 and 4. So in 3, again, this is not a closed interval because it is open at 2. Since it's opened at 2, we are not guaranteed a max or a min. However, looking at this, I can see at 5 on Y, it is the highest point in that relative area. Therefore, I have a max at 0, 5. And then in 4, that graph is continuous. It has a closed interval. Therefore, I am guaranteed an absolute max as well as an absolute min. So our textbook doesn't put absolute, it just puts max and min. So we have an absolute max at 1, 2, and an absolute min at 0, -1. And then we also have a local max and local min at -3, 0, and 2, 0. Okay. 5 through 10, I have to show you the answers on a different area, so we'll come back to those, as well as the 11 to 18. So 19 and down below, we have a minimum value in 19 at 1, which occurs when x is 2. 21, there is a local max at -217 and a local min at 4/3, -4/27. In 22, there is none. And I don't know where they hid 20 on me. But I could always do 20 just to give you 20's answer. Okay? So we did 5 to 15, and then we jumped down and did 23 to 30. So hopefully you're checking those answers right now as well. Okay. And I'm going to give you a minute, and we'll talk about the 5 to 15, which is a lot of what yesterday's lesson was. So in yesterday's lesson, we talked a lot about finding if EVT applies or does not apply. So in number 5, EVT can apply, therefore a max and min exist. The max is at B and the min is at C2. And 6, EVT applies, therefore absolute max, absolute min at C and B. 7, EVT does not apply since the function isn't defined on a closed interval. So again, even though EVT does not apply, it doesn't mean we can't have a max or a min. It just means they're not guaranteed. So in 7, you have a max at C, but no minimum. Okay, I'm going to let you read through 8, 9, and 10. Okay, and then looking at 11 down to 15. So these were a lot like what we did yesterday, looking at the analytic method to finding extreme value theorem, which means looking without graphing. So in number 11, you have 1 over x plus the natural log of x. Well, the given domain is that x is between 0.5 and, 4. So if my domain is between 0.5 and 4, is that function going to be continuous from 0.5 to 4? Well, the answer is yes, because the natural log only does not exist if x is negative. And 1 over x only does not exist if x is 0. So since we were given an interval that was closed and that graph is continuous, EVT applies. So what we have to do in 11 is find our derivative. So your original function is f of x equals x to the negative 1 plus natural log of x. So you get negative 1 x to the negative 2 plus 1 over x times 1. So I get negative 1 over x squared plus 1 over x. And then I like to get a common denominator, so I'd multiply by x over x. So I get negative 1 plus x all over x squared. And then you have to look at, okay, when does f prime of x equal 0? Or f prime of x does not exist. So it equals 0 when the numerator equals 0. And it does not exist when the denominator equals 0. So I get negative 1 equals negative x, or x equals 1. And then over here I get x equals 0. Well, that's not in the interval, so I can just toss that out. So then I use x equals 1, and I use my endpoints. So I need to know what is f of 0.5, f of 1, and f of 4. So f of 0.5 is 1 over 1/2, which is 2, plus the natural log of 1/2. 1 becomes 1 plus the natural log of 1, and 4 becomes 1/4 plus the natural log of 4. Now, I don't anticipate for you to know your natural logs all that well. So if you needed to type in like the natural log of 2 or the natural log of 4, etc. to get what they are, 2 plus the natural log of 0.5 is 1.3068. 1 plus the natural log of 1 is 1, because natural log of 1 is 0. And then 1/4 plus the natural log of 4 is 1.636. So when I look at this information, I can see that f of 1 is my absolute min, and f of 4 is my absolute max. And I know that because of the extreme value theorem. Now, the local min is also going to occur at 0.5, because our graph for a absolute value is going to increase. So this is a local min. And if I was asking you to use EVT, I really care more about the absolutes. So if you miss the local, that's okay. We're not quite at our total skill level yet to know how to find or determine that completely. Does that help with number 11? That kind of just this section in general? Sure. So similar idea. We have g of x equals e to the negative x from -1 to 1. So what we want to do is find the derivative of g of x to start. So the derivative of g of x is equal to e to the negative x times -1, or negative e to the negative x. And then we need to find for this function where it's equal to 0 or does not exist. So in number 12, this function would equal 0 nowhere, because -1 can't equal 0, and e to the x can't equal 0 within that domain. Therefore, e to the x has no zeros for the denominator or the numerator. So there are no zeros, which means that my absolute max or absolute min can only come from the endpoints. So e to the -1 and e to the 1. Well, we know e to the 1 is like 2.63 blah, blah, blah. E to the -1 would be 1 over 2 point all of that. So it's easy enough to say that the maximum is going to be at -1. And the minimum is at 1. Do you want to see like 15, the trig function? Are we okay with the trig one?
Yeah, could you do that one?
Yep. Okay, so once again, the very first thing I'm doing is finding my derivative. And this would be a chain rule, but the derivative of the inside just happens to be 1. So we don't have to worry too much about that. And then what we have to do is find the zeros of this. So the question becomes, okay, when does the cosine of x plus pi fourth equal 0? So we have to use our inverse trig idea. So it's the inverse cosine of 0 equal to x plus pi fourths. So then the question is, okay, when does the cosine equal 0 as a unit circle value? At what unit circle values is the cosine 0? So cosine is x. So x is 0 at 2 points. It's 0 at pi halves. Exactly. And 3 pi halves. So then I have to replace the inverse cosine with my trig values and solve for x. And that should make sense because pi fourths plus pi fourths would be pi halves, which would be 0. And over here, 3 pi halves minus pi fourths would give you 5 pi fourths. And again, 5 pi fourths plus pi fourths would give you 6 pi fourths, which is 3 halves. So my two critical points are at pi fourths and 5 pi fourths. So critical points and endpoints are my potential absolute max and absolute min. So I have to find f, and our initial value was 0. So I have to find f of 0, f of pi fourths, f of 5 pi fourths, and f of 7 pi fourths. So sine of 0 plus pi fourths is the same as the sine of pi fourths, which is root 2 over 2. Sine of pi fourths plus pi fourths is sine of pi halves, which is 1. Sine of 5 pi fourths would be the sine of 6 pi fourths, or the sine of 3 pi halves, which is -1. And then the sine of 7 pi fourths would be like 7 pi fourths plus pi fourths, which is 8 pi fourths. Well, 8 pi fourths is really 2 pi. And the sine of 2 pi is really 0. So now I can look at these values. Okay, anybody know what root 2 over 2 is? Approximately. Okay, so let's think about the square root of 1. The square root of 1 is, square root of 4 is 2. So the square root of 2 has to be between 1 and 2. So if you take like a number between 1 and 2, like 1.5, and divide it by 2, is that going to be bigger or smaller than 1? Yeah, it's going to be smaller, right? Like, we know that the range of sine is -1 to 1. Why do you look so confused, Cooper? Okay, you're looking around. So my absolute max is going to be at 1 because 1 is greater than root 2 over 2. And my absolute min is at -1, because -1 is smaller than all of the other three values as well. Okay. And then the last couple questions I gave you were the true-false multiple choice standardized test question review. So 45 is false. A local maximum of a continuous function on an open interval is not guaranteed to be f prime of c equals 0. Number 46, if m is a local min and m is a local max of a continuous function f on AB, then m has to be less than m. Justify your answer. All right, so this one, we're given a key word. And that key word is local. Just because it's a max or a min does not mean the min has to be less than the max. These are local. So take, for example, and I know because I want to draw this, I'm going to struggle to draw this. Okay. Take, for example, this graph here. We have a local max. We have a local min. We have a local max. And we have a local min. If this was capital M and this is little m, can my little m be greater than my big M? Yeah. So that also makes number 46 false. The little min does not have to be smaller than the big M. (47) was E. 48 was also E. You guys are happy to know. The AP exam used to be multiple choice questions of 5. They recently changed the calculus exam to be multiple choice questions of 4. So instead of having a 20% guessing correctness, you have a 25. So they have now eliminated answer choice E off the multiple choice for AB exams. So you only have to look at 4 choices, not 5. So that is to your advantage. And 49 is B. Okay? Pretty much EVT. That summarizes the EVT unit, which says that if you have a continuous closed interval, then you are guaranteed an absolute max or an absolute min. That absolute max or absolute min could occur at the critical points or the endpoints. And then if it is not continuous or closed, it's not that you're not guaranteed, it's just literally not guaranteed. It doesn't mean they don't exist. So what I want to do now is give you a 4-minute restroom break, and then we're going to pick up with 4-2. The direction is to identify the key parts, aka the absolute maxes, absolute mins. So, looking at that first graphical example, what would this point right here identify as? What's that point going to identify as? Go ahead, Brooke. Okay, it's a relative max. It is actually also the absolute. This is an even function because both arrows are going down. So this represents an even function in terms of end behavior. So the end behavior is what we would call even. And that makes this on only a relative, but also an absolute. What would the derivative at that point be? What would the derivative at that point be? Go ahead, Chase. 0. Okay? This point right here in the valley is what? That valley point is going to be what? What this point right here be? A relative min, right? Can it be an absolute min? No, why not? Yeah, these points over here are going to be much lower, right? Its derivative, though, however, will still be what? 0. It's the one that says 4-0. Refresher. You got these the other day. Yeah, it's the warm-up from like the other, but it's in that packet. Yeah. Okay.
But it's different from the 4-0.
Yeah, well, he was looking for the packet, so I was telling him what the title on the packet was. But yes, it's in the notes guide that I gave you. All right, and then the last mountain peak right here. It's got like my, no, that's not the right packet. That's not the guide. That's not the note guide, I don't think. I passed them out. Or Chase, no, Carson passed them out, didn't he?
Oh, yeah, you left because you were busted.
Sorry.
It's like 5 or 6 pages in.
Alright. If the original function is increasing, what does that tell me about my derivative? It has to be what? Positive. So this derivative is somewhere above that dot. If the derivative, or if the original is decreasing, my derivative is negative. And if my original is increasing, then we have a positive. Derivative is decreasing, negative. So that graph here, this would represent the derivative of that function. So if this is f of x, this graph here is f prime of x. What do you notice about this function? Its end behavior was even. What's the end behavior of its derivative? Come on, Miss Lacey used to do a disco dance for you. If one's going up and one's going down, then the end behavior is opposite, therefore it is odd. Somebody might have said it, but it's like really difficult to hear. You gotta like scream at me. You have on masks, you're facing the wrong direction from me, and there's plexiglass. Alright, how many max or mins did my first graph have? Has 1, 2, 3, right? I heard you, you're good. I'm saying it for the video. How many does its derivative have? 2. How many do you think the next derivative would have? And then the next one? All I heard was bathroom sink. I didn't want to hear any more of that conversation. All right, let's look at one of the funky ones down at the bottom. All right. What do you notice about the beginning and the end? It's closed, right? That's key. Yes. So the difference from the example on the left, the example on the right, are the endpoints. So over in this example, EVT does not apply because it has an open arrow. Over here, EVT does apply because of the endpoints. So this point right here, let's start at the first one. This would be identified as my what? Absolute min. This point here is what? A relative. This point becomes a. This point is. And this point here. I want to talk about the derivatives now. Oh yeah, sorry. I was so excited for my next. The derivative of the relative max would be what? So the derivative of this point would be the derivative of the relative min. The derivative of the absolute max does not exist. Excellent. Why does it not exist? What do we call this type of point? It's a corner. Thank you, Jay. So the relative min derivative here would also be, oh, why didn't I take the endpoints and make them zeros? Exactly. I don't know like what's happening to the left or the right of them. Therefore, even though this is an absolute min in this example, that does not guarantee that the derivative is a zero. So the endpoints are not guaranteed zeros like the relatives in the middle. Does that make sense? Okay. That idea and concept leads us into two new theorems today we're going to discuss. We're primarily focusing on the mean value theorem. Rolle's theorem is kind of like the mean value theorem, but at a specific example. So Rolle's theorem is like the child of the mean value theorem, if that kind of makes sense. So let's get to my notes. Today's students will be able to. So the mean value theorem and Rolle's theorem are ways to identify or interpret what a function is doing around those key points. So it's ways to identify what a function is doing around those key points. So Rolle's theorem states that if I have a function and all three of these statements are true, my function is closed, my function is differentiable. So that last example we just looked at, where it had the corners, Rolle's theorem would not be applicable to that problem because it was not differentiable at all points on that interval. So that would be a case where Rolle's theorem does not apply. And then the last is that f of A has to equal f of B. And this is the one that's different from the mean value theorem. So the mean value theorem and Rolle's theorem have one statement that is different. In this case, that different statement is statement 3. So if all three of these happen, then we can say with a 100% certainty there exists a number C such that C is between A and B and its derivative is equal to 0. Or in other words, we call C a critical point. So we can say with absolute certainty if 1, 2, and 3 are true, I am guaranteed a derivative value equal to C. So let's look at 3 different cases. So on your notes guide, you kind of have like a chart. We're going to fill in that chart for each of these cases. So the first case is linear. So is something linear going to be true? We're going to actually look at 2 cases. So in the top box, you can put your graph. Or in the top box, you can put the words. And in the bottom graph box, you can put your graph. But essentially, I made it that you could like graph it and put the words. And I would just choose what you do now because we're going to have graphs and words for each of the next 3 examples. So this represents something that is continuous. Is that differentiable? Yes. F of A is equal to K. F of B is equal to K. Therefore, every point on AB has a derivative value of 0. In order for it to be linear and f of A equal f of B, all derivative values have to be 0. It's the only possible linear application in which A would equal B. And every point be differentiable. Because if I made it go down for C, then I would have an absolute value and the tip would not be differentiable. This is where Rolle's theorem is limited in its application. Rolle's theorem is limited in the application because of statement 3 being that f of A has to equal f of B. You can totally move to a different seat if his head's in your way. It's all Tim's fault. Kind of lift it up, but not a lot. Better a little bit? All right, number 2, we have a parabola. A parabola is going to be continuous. It's differentiable. And you could draw it in a way that A and B are both at K. And remember that C does not have to be the middle of A and B. In this case, it is, but again, it does not have to be. You could draw your parabola in a way that A and B, again, doesn't matter how you draw it, but you could draw it in a way that A and B still matched up, but maybe the peak is like over here, and ooh, that's really difficult to do with a mouse. But you do not have to make it in a way that it is perfectly symmetric about them. So just try to line up your C as best you can so that C represents that maximum. And then if f prime of C is equal to 0, which we know it would be because that's a max. Let's pause because I can get. Then we also know that f of C is greater than f of A. What if it was drawn the other way? Could we say that if the graph came down, f of C, instead of always being greater, f of C would always be what? Less than, right? So it just totally depends on where your graph is drawn. If it's open up or open down, this would change respectively. And therefore, f has an extreme value by the extreme value theorem. So all we're guaranteed by Rolle's theorem is that we have an extreme value. It could be a max or a min. It's different from EVT in the sense that it is guaranteeing the 0 of the derivative. It's not guaranteeing the extreme value. It is guaranteeing the 0 of the derivative. That is the key point of Rolle's theorem, that the derivative is equal to 0. Rolle's theorem guarantees a 0 of the derivative. Like if you want a summary statement, Rolle's theorem guarantees a 0 of the derivative. What? Yeah, it was me. I asked Nick, who was like listening live, if he could hear me okay. So then it also went to, like, I have Zoom open on like 5 devices right now. One for recording, one for projecting, and one for writing. All right. So those are the cases where you have a graph. But we know in calculus and or in math that oftentimes we aren't given a graph. We're oftentimes given an equation. Not a clue. Well, and that is why I opened Zoom on like 100 devices. Let's go to the Apple iPad. Okay. So it says verify . So we need to verify in the next example, given an equation, how Rolle's theorem could apply. So what we have to do is confirm that the first few statements are true. So is f of x going to be continuous from 0 to 2? The answer is yes. F is continuous from 0 to 2. We know this because f of x is a cubic polynomial, and polynomials are continuous. I know that because it is a cubic polynomial and polynomials are continuous. Number 2, is it differentiable? Yes. And again, it's differentiable because it is a cubic, and cubics are differentiable on their domains. Number 3, does f of a equal f of b? Well, this one's a little bit trickier. I need to know what is f of 0 and what is f of 2. So f of 0 is 0 cubed minus 3 times 0 squared plus 2 times 0 plus 5, aka f of 0 is 5. F of 2 is 2 cubed minus 3 times 2 squared plus 2 times 2 plus 5. So 2 cubed is 8, 2 squared is 4, 4 times negative 3 is negative 12, 4 plus 5, well 8 plus 4 is 12, 12 minus 12 is 0, so that zeroes out, and then we are left with 5. So f of a equals f of b. Therefore, I have all 3 conditions of Rolle's theorem satisfied. So if all 3 conditions of Rolle's theorem are satisfied, then it says to find all values of c that satisfy that. Well, what that means is I need to find when f prime of c equals 0, which means I need f prime of c. F prime of c is really the derivative of f of x, but instead of x's, we have c's. So that gives 3c squared minus 6c plus 2. And I need to know when does that equal 0. So I look at that and I say, okay, can I factor that? So 3 times 2 is 6. I need factors of 6 that sum to negative 6. Can you have factors of 6 that sum to negative 6? No, because you had 6 and 1, 2 and 3, doesn't work. Therefore, if we have a quadratic that's not factorable, how do I solve it? How do you solve a quadratic that's not factorable? Quadratic formula, thank you. So C equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And to think you thought when you learned that in Algebra 2 you were never going to use it again. 4 times 3 is 12. 12 times 2 is 24. 36 minus 24 is 12. All over 6. Well, 6 divided by 6 is 1. 12 divided by 6 is 2. So we get 1 plus, sorry. If I'm going to bring my 2 in, I forgot I have to make it, whoa. I did not hit clear. 6 divided by 6. There we go. Is 1. 12, you can take out the 4. So you get 2 square roots of 3 all over 6. And that's where I was trying to say that 2 divided by 6, not 12, is 1/3. And over with my root 3. So you get 1 plus or minus the square root of 3 over 3. Leave it. All it asks me to do is find the values of C that satisfy that conclusion. These are the values of C. Those are the critical points at which f prime of C equals 0. These are the C values where the derivative is 0. What does that mean they are on the original? What does that mean they are on the original? They're the critical points of the derivative. What are they on the original? Yeah, they're my relative extrema. So I told you we were going to learn about 2 theorems today. We learned about Rolle's theorem. Now we're going to learn about the mean value theorem. If you go back to the word mean, the word mean, when we learned about it in Algebra 1, when you learned about it in geometry, when you learned about it in statistics, mean in math doesn't mean angry. Mean means what? Average. So it's kind of like the average value theorem. This is the average slope. The mean value theorem is critically important in calculus. The mean value theorem is the point at which the instantaneous slope equals the average slope. The mean value theorem is the point at which the instantaneous equals the average. So if you're using physics words, the mean value theorem finds the point at which the instantaneous velocity equals the average velocity. The mean value gives the point at which the instantaneous equals the average. I already told you that conditions 1 and 2 for Rolle's and mean value theorem are the same. Condition 3 does not exist in the mean value theorem. If 1 and 2 are true, then the mean value theorem says that there exists a point C in which the derivative has to equal the slope of the secant. The mean value theorem guarantees there exists a point at which the derivative equals the average. So slope of the tan equals slope of the secant. Slope of the tan equals slope of the secant. you will hear me say MVT. You can guarantee there is an MVT question on the AP exam. Guaranteed. So example number 2 says determine all of the numbers C which satisfy the conclusion of the mean value theorem for the following function. We need to first go through and check, is this function continuous? Yeah. Is this function differentiable? Okay, 1 second. My iPad got booted. There we go. All right. So it is continuous. It is differentiable. What I want you to do now is find the derivative of f of x. Find the derivative of f of x. Okay. Find the derivative of f of x. And my iPad just got booted because the school Wi-Fi is awesome. So I'm sorry I can't write with you this time because my iPad keeps getting booted out of the Zoom meeting. So we know it's continuous. We know it's differentiable. You found its derivative. So the derivative of this function is 3c squared plus 4c minus 1. What we're going to do now is find where f of b minus f of a, or the slope of the secant, is. So I want you to find the slope of the secant. So that's f of 2 minus f of 1 all over 2 minus 1, which is 8 plus 8 minus 2, minus 2 all over 3. So again, we start with, is it continuous? Then, is it differentiable? Then, if both of those are true, you find the slope of the secant. So in this case, the slope of the secant was 4. That's my f prime of c. So we want to know when the slope of the tangent equals the slope of the secant. So that's when your derivative equals 4, and then you solve your derivative. Remember, anytime you're solving a quadratic, it must be set equal to 0. Once again, this is not factorable, so I use the quadratic formula. And these values down here are the points at which the slope of the secant equals the slope of the tangent, or the slope of the tangent equals the slope of the secant, yeah. And those points have to live in my interval. So the negative is not going to live in my interval. So the final condition I could get it to zoom up, there you go. Or your end answer is only the positive point. It is only the positive. I don't know why the board won't show you that answer. It is only the positive point. So you have to eliminate the negative for your final answer. Whoa. Oh, there you go. So it is only the positive because the negative does not exist in that closed interval. The negative would be outside that interval. Okay? Let's look at an example in which the mean value theorem fails. Just like EVT can fail, so can the mean value theorem. An absolute value is an example with which the mean value theorem would fail. An absolute value is an example with which the mean value would fail. This becomes an absolute value because this is a condition in which it's even, and the simplification is odd. So when you have an even powered exponent to an even nth root, and that answer becomes odd, you need an absolute value. So it's like if you take the square root of 6, that becomes x cubed, you'd need absolute values on that cubic. Because when you take x cubed and plug a negative number in, it could become negative. But if you take a number to the 6th power, you know it's always positive. So that's why you get absolute values with this, because you cannot get a negative under a square root. The squared gives you that domain, but then when you clear out the squared and the square roots, you get x, and that negative would kind of be able to occur, and that's why we put the absolute values on it. So we know that that's not differentiable at 0 because there's a sharp corner, and we cannot take the derivative of a sharp corner because the slope from the left does not equal the slope from the right. The second example will also fail. The second example is going to fail because you have to always check a piecewise for continuity. So if I were to roughly graph this example fails because the limit from the left and the limit from the right do not align. If the left-hand limit doesn't equal the right-hand limit, then the limit does not exist and the function is not continuous. So it's not continuous at x equals 1. Since it's not continuous, it fails MVT. This would also be conditioned as not differentiable because we have a jump discontinuity. This function would also not be differentiable because you have jump discontinuity. So to summarize all of that, the mean value theorem helps us identify where a graph is rising or falling. A function can be defined on an interval I if f on I increases, and you need to write down what I scribbled under. If x1 is less than x2, it implies f of x1 is less than f of x2. So again, we're under interpreting the mean value theorem. And we're going to pick up a lot with this tomorrow, because the application of the mean value theorem is almost as important as interpreting what it tells me. So 4.3 in our textbook is all about what does that mean value tell us. So if we have a continuous closed interval and it's continuous on AB and differentiable on AB, then our derivative is greater than 0 if f increases. Our derivative is less than 0 if f decreases. And that's what we talked about with those graphs at the very beginning. I asked you, okay, the function is increasing. What's my derivative doing? The function is decreasing. What's my derivative doing? Mean value helps us find those points. Mean value helps us find those points. So again, you can kind of just put an X over this example. We're going to do this in 4.3. So because today's lesson was rather long, I just want you to put an X on that, and we're going to get into this in 4.3 very in-depthly. So you don't have to worry about it today. So what I want to do for your assignment, and I know some of you sent me the homework for the other assignment, that's fine. I wasn't actually checking it, knowing we were going through everything today so closely. And I've been checking a lot recently. We are continuing into the next part of the section, so I just want you to get a taste of Rolle's theorem and a taste of mean value for tomorrow. So let's do page 202, 1 to 21 odds. So it's like 11 problems. Today was a long lesson. I know that. I want to be able to get a taste of that. I won't collect this homework just yet, so there's no Dropbox due tomorrow morning. Not saying I won't collect it in the future, just not tomorrow, but I do want you to be able to come in tomorrow and we're going to talk about some of this.